All right, so welcome back again to Vector Calc. We're going to continue our discussion of multiple integrals today, but now we're going to start turning our attention to triple integrals. So we've done a bunch with doubles, and we've seen how if we change to polar coordinates, it can actually help us out a lot, depending upon the function or the region. Well, now we're going to start looking at triple integrals. So triple integral, same idea, just more. All right. But before we get into that, as always, let me just open it up for any questions about homework or anything else that we've talked about. Any questions before we move on to triple integrals? All right. Well, hearing and seeing none, we'll go ahead and get moving. So I'm just going to go ahead and hop to the whiteboard. So I'll be with you in just one moment. All right. So triple integrals. What's the deal with these guys? How do they behave? How do they work? What do they do? Well, let's just start with definition. All right. Well, first of all, what they're going to look like when we have a triple integral is going to look just like with our double integral. But now we've got three, right? We've got three integrals, which means we need three differentials. So I'm going to go ahead and make one with a specific order of differentials. But let's call this guy f at f of x, y, z. And I'm going to start with, say, dz, dy, dx. That's actually just one of 6 ways that you can represent a triple integral with differentials. If we just have the letters z, y, and x, it's all the different ways you could order those. So dz, dy, dx, dz, dx, dy, dy, dz, dx, dy, dx, dz, dx, dy, dz, dx, dz, dy, I think, or all 6. Right, so now we have lots of options. With double integrals, there were only 2. There was dy dx or dx dy. Now we've got 3. We have 6. Sorry, so we have 6 with the 3 variables. You know what? I just turned on my light. I don't think that helps. It's bad there. We'll just go with this light as it is. All right. Anyway, so there are 6 different ways, but here's a specific way. Now, when it comes to the bounds, we know to interpret this kind of the same way, that these inner bounds, those are going to be z equals. And I know that they're z equals because the innermost differential is dz, right? Which then means the next ones out are going to be y equals. Again, because of the fact that we had y's, and then this last one will be x equals. So exactly the same idea as what we saw with the other ones, with the double integrals. We just now have 3. But here's the first thing that's a little bit different. So we saw that those inner integrals, those inner bounds on the inner integral, could be functions, and they still are. They still can be functions, but this is where it gets a little more complicated. Think about how I have this set up. The first one is a dz. That means these z equals, they can actually be functions of both x and y. So these innermost bounds are actually going to be functions that are multivariable. So I'm going to call them g1 of x comma y and g2 of xy. So g will be the name of those functions. We'll have g1 and g2 as our 2 different bounds. Okay, so basically, when we integrate this, it's going to be a partial integral, so only the z's are variables, everything else is constant. But then we're going to substitute in for our z's, and we're going to put in a g1 and a g2. they will have x's and y's. And at this point, it turns into just a good old double integral like we've seen the last week, basically. So the bounds then on y, those are also going to be functions. I'm going to call these guys h. And in this specific case, h1 and h2, they're going to be functions of x, because that's the only variable that's going to be in there that's not a y. And then once we integrate that, right, the y's are the variables, the x's are constants, we substitute in for the y's, we're left with just a function of x that we're going to integrate with respect to x. And so then these bounds are just going to be plain old numbers again, a and b. So if you look at the outer two, it's exactly like what we saw before in terms of their bounds. We just now have a third one, and that third one can actually have functions of two variables. All right, well, it should kind of make sense. And you can imagine if this went to a fourth integral, like if we went for a quadruple integral. Okay, so we throw on one more integral sign, and the next innermost one is now going to be with bounds of functions of the three other variables. We'd have to have a fourth differential. You want a fifth one, a sixth one, a seventh one, that's fine. We can keep doing this all day long. It's just each layer in here, each layer of the onion, each time we go in, our bounds get one more variable as a possibility in terms of those functions. All right, so let me just show you one. Let's do one. So you can see how this works, and you can see that it's not that really big of a deal. It's just a matter of recognizing how these behave. So here we go. Let's go with triple integral. Let's say that this goes from 0 to 1. Let's go from x to x squared. And then we're going to have x minus y, y plus 1. The function that we're going to integrate, let's just be kind of boring here and make it x, y, z. And now the order of integration for this one, we actually could probably figure it out. Let's see if we can. Go to the innermost bounds, and you see which variables are in here. There's x's and y's, which tells me that our first differential is going to be a z, dz. Okay, so once we substitute those in, this next integral is only in terms of x, which tells me I need the other letter. So that'll be a dy, and then finally dx. All right, so here's an example of one. Let's actually just work through it so you can see the process. But you'll see that the process, yeah, that's not that complicated. All right, so we start here, and z's are variables. Everything else is a constant. So when we do that integral, this is going to give us the outer two integrals still the same, 0, 1, x and x squared. But now we're going to get xy, those are constants, constant multiples. The z becomes z squared over 2 that we're going to evaluate at x minus y and y plus 1. So we'll go ahead and put those bounds in. We're going to get xy times y plus 1 squared over 2 minus xy times x minus y squared over 2 dy dx. So there was our first step. We just dealt with the z's. We plugged in with the z's, those innermost bounds, and now we're here. But now this is exactly what we've been doing the last 2 weeks. Now we're going to integrate this with respect to y. Everything that's not y is going to be constant. Substitute in for our x's, and so on and so forth. So let's just go ahead for the sake of it. Let's finish this guy off. I'm going to distribute. When I distribute through, I'm going to get an xy cubed plus 2xy squared plus y, that's all over 2, minus x cubed y minus 2x squared y squared minus, or sorry, plus xy cubed over 2. And now we're ready to integrate that guy with respect to y. I'm going to pull the 1/2 all the way out front, just to make life easy for us, or easier. So we're going to get xy to the 4th over 4 plus 2xy cubed over 3 plus y squared over 2 minus x cubed y squared over 2 plus 2x squared y cubed over 3 minus xy to the 4th over 4 that we still need to evaluate at x and x squared. All right, so putting in those bounds, you can already see how old this gets. But let's see, when we plug in x squared, we're going to get x to the 9th over 4 plus 2x to the 7th over 3 plus x to the 4th over 2. I'm going to start combining these things, kind of lining them up so that we get the same powers together. When I plug in x squared here, I'm going to get minus x squared to the 7 over 2. That's going to give me an x to the 8th, so I don't have any of those yet. So plus 2x to the 8th over 3. And then I'm going to get a minus x to the 9th over 4. So that was from plugging in the x squareds. Plugging in the x's, I'm going to get a minus, oh good lord, x to the 5th over 4 minus 2x to the 4th x to the 4th over 3 then I'm going to get minus x squared over 2. I don't have any x squared yet. Then I'm going to get a plus x to the 5th over 2. I'm going to get a minus 2x to the 5th over 3. And then a plus x to the 5th over 4. So I'm pretty sure I got those things all lined up by powers. So let's just see what we end up with. The x to the 9ths are gone. X to the 8ths, I've got 2/3. X to the 7ths, 2/3 minus a half. That's 1/6. So 9, 8, 7. Then we got fifths. Those guys cancel. A half minus 2/3 is minus 1/6 x to the 5th. And then fourths 1/2 minus 2/3. Again, I believe that's a minus 1/6 x to the 4th. And then lastly, the minus x squared over 2. Whew. So all of that algebra brings us here, but now it's just good old single variable. It's just algebra, boys. It's not that big of a deal. And I also noticed this is really weird for me to see me on screen, by the way, because now I totally see what you guys see. And I noticed that my writing goes, it's got a negative slope, even though to me it feels like it's straight across. The weird musings of Bruce as he does this stuff. All right, well, anyway, so let's just
gonna
bang
suck
this
at
guy
it's on
out.
a test.
Yeah, really? Come on.
I'm gonna have
it's
to
not
write
that
all
bad.
this out.
Well, let's just finish this. We're almost there, right? So we get 2x to the 9th over 27 plus 148 x to the 8 minus 136 x to the 6th minus 124th x to the 5th minus x cubed over 6, evaluated at 0 and 1. Luckily, the zeros just are going to give a 0. So 2/27 plus 148 minus 136 minus 124th minus 1/6. And I'll let you do your fraction addition and subtraction to get a final answer. Okay, so it was a seemingly not big deal function, right? X times y times z. And the bounds weren't terrible, but you do see how much is actually involved here. But look at the process. The process, as opposed to double integrals, is the same. It's just there's one more level, there's one more thing on the inside that we have to do. Okay, so are they going to be a pain in the ass? Absolutely. That's going to happen. But they're definitely doable. And as we know, for mathematicians, that's what matters. Can we do it? And the answer is yes, we can. All right, so that's how to do a triple integral. So now the question is, where are they coming from? What are we actually doing? What do we use them for? And so on. Give me 1 second. I'm going to see if I can adjust the screen here in my room. I actually should probably ask you guys. I noticed the brightness of my screen getting like brighter or darker kind of randomly. Is that coming across in your video feed, or is it just my camera?
No, it's just the monitor settings.
Okay, cool. Well, then that actually makes me a lot happier. All right. Anyway, so what are we actually doing with triple integrals? What's the process? Well, think about single integral. We were basically adding up a function over an interval. For the double integrals, we are adding up a function over a region in the plane, right? We specify a region in the plane. Well, a triple integral, that's adding up the function's value over a solid in space. Okay, so here's kind of the idea. Imagine we've got a solid in space, and I'll even try to make it relatively nice, right? So just a box. Let's just say we've got a box. And inside that box are all kinds of points, x, y, z's. And the function is going to take on a specific value for every one of those points in the box, right? Like even if you think about the one that we just did, we looked at that triple integral of x, y, z. You can imagine if, say, these are our coordinate axes, right? So this box is somewhere up in here. You take one of those points, you plug in x, y, z, you get a function number. And that's going to be true at every point that lies within the box, right? Okay, so here's basically what's going on. We're taking that solid, this solid, and we're going to break it up into a bunch of little rectangular pieces. The volume of each one of those is going to be a dx times dy times dz, because that's the volume of a box, right? Length times width times height. So basically what we're doing, like we've always done, is we're taking the function and we're multiplying it by the volume of that box. Then we're adding them all up. So we're really getting a triple integral, or sorry, a triple sum of fxi yj zk times delta xi delta yj delta zk. The I, j, and k are just allowing for different possible sizes in the 3 different dimensions. And then we're going to go from 1 to infinity for all of those pieces. So it's exactly the same idea. Break it up into a bunch of infinitesimally thin chunks, multiply those by the function. It's just now these infinitesimally small chunks are little volumes. And so when you do that, what you end up then with is the triple integral. But I'm going to put a generic dv instead of dA, right? When we did double integrals, we just put dA. Those are a little area chunk. Now this is a volume chunk. And then we're integrating over a region in space, or a volume in space, solid in space. And I'm going to use Q for that. So you know how I used R for a 2-dimensional region? I'm going to use Q for the 3-dimensional region. So it's really the same idea. It's just getting this. All right, so now the question is, what is it actually finding, right? Like a single integral, you were taught that's finding the area under the curve. We go to the double integral, it's finding the volume under the surface. Okay, so then what's a triple integral do? Well, now you can't use geometry because now we have to be in a fourth dimensional world, right? Think about it. When we had a variable of one function or a function of one variable, just the x's, right? We had to go to x's and y's to draw the picture of it, right? Can't draw y equals x squared without going to 2D. When we went to two variables, okay, now we needed a third dimension, right? We've got the surface in space. We plug in our x and y, we get a z value. All right, well, now we're plugging in an x, y, and z, and we're getting out another value, a w, a t, or whatever you want to call it, right? So I just saw that Victor threw in the chat box time. That is often thought of as fourth dimension, especially in the physics realm, because we talk about space-time and how they're all integrated. So you got the three spatial dimensions and time. But geometrically, is there a fourth dimension? Yeah, I'm sure. It's just we can't see it, right? We as humans, we are bound to this three-dimensional world. This is our viewpoint. And so trying to picture a fourth dimension just doesn't really work. But basically think the three dimensions we've got and then extend them out in another dimension. And that other dimension just needs to be orthogonal to all three of our spatial dimensions. Please don't try to picture it because you can't.
I tried. How'd you know?
And does your brain hurt because of that?
Yeah, I don't even know where to begin.
Yeah. And that's just the reality of it is like, no matter what dimension you're in, you can always visualize smaller dimensions, right? Dimensions that are same size as yours or lower. Like for us, we live in the 3D world, but it's really easy to understand 2D. We do it all the time. We draw it on the whiteboard or on your paper. We also understand 1D, right? One dimensions. Just go that way. Yeah, no problem. I can picture that. I can even picture 0 dimensions. It's boring. It's just a point, right? But I have an understanding of all of those because those reside in our world. Lower dimensions reside in higher dimensional space, right? So if we wanted to actually be able to visualize the fourth dimension, we'd have to either live in the fourth dimension or live in a higher dimensional world. Fifth dimension, sixth dimension, seventh dimension, and so on. This whole idea of higher dimensions, you're going to run into a lot next quarter when you take linear algebra. It's kind of one of the key things that we do. But I'm just going to give you some advice. Don't try to picture it. Don't try to physically model it because you can't. I know that there are some people that claim that they can, we'll talk about the fourth dimension. You know how you have a cube that comes from a square? Well, the fourth dimension is what we call a hypercube, and there are ways of modeling hypercubes in 3 dimensions, just like I can model 3-dimensional cube in 2 dimensions and so on. So some people will do that, will construct in 3 dimensions a model of a hypercube, and that's great, but you can't picture it because you have no idea what a hypercube actually looks like. Right. So basically, the moral of the story is, what is this thing doing? Well, it's adding up this function over all the points in this region of space. That's what it's doing. What is that quantity? What's the name of that quantity? I don't know. There might be a name for the fourth dimensional equivalent of volume. I mean, that's what it is. It's the fourth dimensional equivalent of volume. But to me, that's meaningless. It's absolutely meaningless. Now, that doesn't mean triple integrals aren't useful. That's not at all what I'm saying, because there are plenty of times that we want to add up functions over 3 dimensions. It's not necessarily going to give us something geometric. Like another good example, think like in one single variables. right? Something else that we use single integrals to do was to calculate arc length, let's say. And arc length totally lives in one dimension. So if you were a one-dimensional creature and someone wanted to talk about the arc length of something, you go, oh yeah, totally. Right? Well, we're going to use this anytime we want to do something in 3 dimensions. So just a real quick example for those of you that are in physics. One of the theorems we're going to develop later is going to allow us to calculate flux, which is when something is flowing through a surface. So in terms of you physics folks, have you talked about electrical flux or magnetic flux yet?
Yeah.
Yes, a lot.
Okay. So it's basically looking at like how much of the charge flows through a surface or whatever. Well, if you've got a closed surface, right? If you've got a closed surface, then you can actually calculate that flux by looking at a triple integral of the volume on the inside, right? And so there are lots of applications of triple integrals, but again, in terms of a geometric, what's it doing? Nope, don't even go there. Just realize that it just is what it is. It's doing the same thing as a double integral, just one dimension more. Just like a double integral is doing the same thing of a single integral, one dimension more. The problem is we run out of dimensions and we can't picture it anymore. Let me recommend you guys a book. It's called Flatland. It's a super quick read. It's not very big. I'm sure you can find it for free. Like to throw in your Kindle or something, because it's kind of old and it's relatively cheap. But it's called Flatland, and it's actually a story about creatures that live in 2 dimensions, and they're all shapes, right? So like circles and triangles and all that good stuff, and they live in the 2-dimensional world, and so they talk about the experience of living in 2D. If you read that, it will help, I think, you start seeing what I'm talking about in this 3rd dimension, but it's not something that we really think about much. And it gets very philosophical, but I would definitely check it out. So Jacob, you said that there's a movie adaptation. I've not seen that. Is it animated, or have you even seen it, or you just know of it? All right, so it's an animated movie. I'm definitely going to have to check that out. But anyway, it's probably worth checking this book out at some point when you've got a little time. Like I said, it's a fast read, and it was written by a mathematician, obviously. So kind of interesting kind of thought experiment to think about how their view of the world is. And then you start thinking about how you're looking at them in 2 dimensions and thinking, man, they've got it all wrong, or they're not seeing the whole picture. Then start thinking that, well, maybe there are like 4th dimensional beings that look at us living in this 3 dimensions, and they're like, man, they just really don't get it. They don't see the whole picture. And it makes you start realizing that, well, if you guys haven't figured this out about me yet, I'm definitely one of those people that's like, yeah, humanity, we are not all that. We think we're so awesome, but we're not. And there's so much about this universe that we have no understanding of, that we'll never get an understanding of. And to think that we know everything is the ultimate in hubris. Like, that's where I am. Now, don't take that as you suck, because that's not what I mean, right? People are awesome, and individual people are awesome. But as a whole, we tend to overinflate our importance. And that causes lots of problems, in my opinion. Anyway, I'm starting to preach, so let me get off my soapbox. So let's get back to triple integrals. Now, one of the things that we definitely can use them for is to calculate volumes. Just like double integrals can calculate areas, single integrals can calculate lengths. We can actually do the exact same thing with triple integrals. So I do want to go ahead and just give you an example of where we could use this. And that's to find volumes. Okay, so basically, if you want to find the volume of some spatial region Q, okay, so volume of the solid Q, what you're going to do is you're going to integrate over that region 1. You're just going to integrate 1 dV. Just like with areas, we talked about that, I think, I don't know if it was last time or 2 times ago, when we were looking at areas in double integrals, we could just integrate 1 dA. Well, it's the same thing, because if we integrate dV over a given solid, we get the volume of that solid. So really the trick is going to be, how do we set up the bounds? Because if we can get the bounds, then it'll be easy enough for us to calculate those volumes and be good to go. So let's start easy. Let's start really easy. And let's calculate the volume of a box. But we're going to do it using a triple integral. Like, I already know you guys know how to calculate the volume of a box, right? Length times width times height. You calculate those 3, you multiply them together. But I want to show you how using triple integrals will get you to that same place. So, as such, how about we look at this example? Let's find the volume of the box. So here's my 3-dimensional world here. And this box is going to be living here in space. I'll give you some bounds here in a second. Right, so there's our 3-dimensional box. It's kind of living up there. And here are the coordinates of the vertices. Okay, so these corner points here are their coordinates. So this bottom corner right here is 1, 2, 3. So that's saying we're going 1 in the x direction, which on my graph, when I do one of these kind of standard graphs, I'm going to do it like this, x, y, and z. So x is to the right like we're used to, z is up because that's kind of standard what we like up to be, and then that means that y has to be coming, totally lied to you. This one, the x is going to be coming outward, x, y, z. Okay, so that's going to kind of be my standard when I draw it like this. If I don't put on a 3rd dimension and I use just plain old x and y, z is going to be coming out of the board. All right, but I will always try to label them so that you know what's what. Okay, so that means that this point, we went right 1, or we came out on 1 on the x, we went over to 2 on the y, and then we came up to 3 on the z. So this point is actually floating in front of the board. I don't know if you can see with depth perception through your video, but it would be somewhere out here. So it's actually living out in that general area. Okay, so there's that one. So that's 1, 2, 3. Some other points, just so that we've got them. This next point down here is 1, 6, 3. That's that one. And I think if I just give you one more point, we'll be able to know what everything else is. This one is going to be -2, 6, 5. So it's actually back in the x direction, out here in the positive y and then the positive z. I don't want to give you the coordinates of all 8 points because then I think it's just going to get muddled up and we won't be able to see everything. All right, so far so good?
Yeah.
Here's my question. Can you tell me what the volume is right now without a triple
Yes.
integral?
Yes.
What is it? I mean, in essence, we just need to know the lengths of the sides, right? So Seamus should put 4 times 3 times 2. Victor put 20, which one of those can't be correct, right? Since they're different. But let's just see what the different lengths are. So this length right here is length 4, because the y is changing from 2 to 6. The vertical is 2, because we're going from 3 to 5. And then the one that's going in and out of the board, it's length 3, because it's going from -2 to +1. So this box is 4 by 2 by 3. So we know that its volume should be 24 cubic whatevers, 24 cubic meters, cubic inches, cubic light years, like who knows, whatever. Okay, so we know its volume. We don't need a triple integral. But let's see if we can set up a triple integral to do this.
24 cubic light years would be huge.
Yeah, that would be an incredibly large space. Although, I mean, it'd be huge, but minute compared to the universe.
Yeah.
I
Crazy.
mean, it's relative to scale, right? But yeah, to us, that would be insane distances. But you can fit a lot of stars in there. I'll tell you what. Obviously, it just depends where we are. All right, so let's see if we can set up this triple integral. So we already know that we just need to integrate 1. So let's do that. But what we do need to decide is which order of integration. Now, I'm going to help you see how we could set this up in different ways. But let's start with that dz, dy, dx. This is going to be the one that you use primarily, just because. When we usually visualize stuff in 3 dimensions, it tends to be the z surface that's a funkier, but it totally can be any way. Okay. So we'll do dz, dy, dx. All right, now we need to talk about integration man for triple integrals. So remember what integration man did before, right? He just like stretched himself up and down and then walked in the other direction. Right, so I was going with vertical integration in horizontal. He stretches himself left and right and then works his way up and down. Okay, now integration man in 3D does kind of similar thing, right? So the way that we've got it with dz, he's going to be standing upright in the z direction. And his head is going to bump up against the surface that's on top. Now, in this case with the box, that means integration man's going to be standing in the z direction, so upright. So his head would be on the top of this box and his feet would be at the bottom. Well, he's going to be in different places within this box. I'll try to put a few of them in here. All right, but always he's going to end up walking around in all these different directions. But z is going to determine the direction of his head and his feet. So that's why with my z-axis, he's upright in this picture. Okay, so we need to think about the surfaces that he's walking on. So since this is a box, his feet are always on the bottom of the box. And what's the equation for that box? Or sorry, not that box, that surface, the bottom.
XY?
Not XY. Remember, it needs to be a Z equals. So think about the bottom surface. The equation of this is going to be given by what? Z equals. All right, good. Victor just put in the chat box, Z equals 3. So his feet are always on Z equals 3. Look at these points. The 1, 2, 3, 1, 6, 3. The other ones is going to be a -2, 6, 3, -2, 2, 3, and all the other ones. The X's and Y's are going to change, but the Z is always 3. So in 3 dimensions, if you have X equals, Y equals, or Z equals, those are planes. And those are planes that are parallel to the coordinate plane. So Z equals 3 is parallel to the XY plane. It's just up at 3. So the coordinates for his feet or the function that describes the surface of his feet is 3. Okay, so what about his head? And I'll tell you what, Seamus, now you gave me yours that you gave me earlier. So Victor just put in the chat box z equals 5. So Seamus put that in earlier. But that's where his head is. His head is at another plane that's parallel to the xy plane. It's just z equals 5. Okay, well, imagine that this wasn't a box, but like, let's say the top had like a dome. So maybe there's like a semicircle, or a circular, spherical surface there. Well, you take the equation of that sphere and you solve it for z. That's what's going to go up here. Or you've got a paraboloid, solve it for z, put that on top. Or it's a slanted plane, solve it for z, put that on top, right? It doesn't matter. Whatever that surface is, we just write it as z equals, and that's where his head's going to be. Okay, so that's the first step for integration, man. So now that we took care of that, we go back to dy dx. Well, that's the same thing that we did before. We look at what is the shadow of this surface in the xy plane. So let me actually draw that shadow in the xy plane. So if I were to bring this thing down into the xy plane, right, my picture is maybe not going to be all that perfect here, but so there's going to be the point 1, 2. That's going to come up here to 1, 6. And then these are going to be minus 2, 6. And minus 2, 2. So are you guys all cool with what I'm talking about? Like that would be, if we were to shine a light on this box, we'd see the shadow down on the xy plane right here. Let me draw it the way you're used to seeing it in xy. So there's the picture. Bradley, I'm going to mute you real quick.
My bad.
No worries. All right, so this is basically that rectangle, but on the xy plane, right? So the box was out here. We're shining the light on the box. We see the shadow. So for the dy dx now, this is the same thing we did before. So since I've got dy first, that means I've got a vertical integration man in this picture. And we see that his head is always on y equals 6. And his feet are always on y equals 2. So those would be our bounds here. So from 2 to 6. And then the x's, we see that the x's are going to range from minus 2 to 1. So here would be the setup with triple integrals. The z's are going from 3 to 5, the y's are going from 2 to 6, and the x's are going to go from minus 2 to 1. And anytime your bounds are all constants, your region in space, your solid in space, is a box. Just like when the bounds were constant in 2 dimensions, it was a rectangle. Okay, so it's kind of the same idea here. All right, well, let's run this integral and let's see that we get 24. So we start by integrating with respect to z. Well, integrating 1 with respect to z gives us z that we're going to evaluate from 3 to 5. Well, if you use the fundamental theorem, 5 minus 3 is 2. So we get the integral from minus 2 to 1, 2 to 6 of 2 dy dx. All right, well, integrating 2 with respect to y gives us 2y. that we need to evaluate from 2 to 6? Well, plug in 6, we get 12. Plug in 2, we get 4. 12 minus 4 is 8. So we now have the integral from minus 2 to 1 of 8 dx. Well, that's 8x evaluated at minus 2 and 1. 8 minus negative 16 is 24. So you notice that we do get exactly the same thing. We would never do it with an integral though, right? If you got a rectangular box and you can figure out the lengths of the 3 sides, you don't bother with the triple integral. But I wanted to walk you through this so you can see what the process is when it's not a box. When we have some other funky shape, how do we go about doing it? All right, so before we go to an example there, questions on this one? Is it kind of making sense? Do you see what's going on?
Yeah, it makes sense.
Okay. All right, so let's try this. We're going to find the volume of a tetrahedron. So a 4-sided shape, right? For those of you who are D&D players, this is your good old 4-sided die, right? A little like pyramid-y looking one. But here's how this tetrahedron is going to play out. Let me put on some coordinate axes here. So again, we got our X, our Y, and our Z. But this tetrahedron is going to be such that it connects these 3 points. Basically, I'm going to give you the vertices of this. So one of them is going to be the origin. That's going to be one corner. Another one is going to be the point up here that's 0, 0, 6. Then there's also going to be a point out here, 2, 0, 0. And then another one out here that's 0, 3, 0. Okay, so those are the 4 corners of this die, of this shape. So if you were to connect the dots, like this triangle that I just drew, this blue triangle, is one of the faces of this tetrahedron. And it's actually out from the board, right? So it's sliding out. The other 3 are the triangles that are in the coordinate planes that connect those with the origin. Okay, so like in the XY plane, there's this little triangle. In the YZ plane, it's this one. XZ plane is that one, and so on. Okay, so I want to know the volume of this tetrahedron. Okay, so not a terrible shape, right? I mean, it's not ugly. It's got nice flat sides, but oh man, it definitely doesn't seem as easy because there's not even like a nice formula. Like for area of a triangle, for example, if you just did base times height times a half, you're done. Well, there isn't the same formula for a tetrahedron, right? Like if you were to take just a regular die, that's a cube, right? And you were to form a tetrahedron by using these corners of a cube, its volume is not half that of the original cube. Okay, so we don't have a super nice formula, unfortunately.
Couldn't you find surface area then integrate it?
Integrating the surface area. Are you thinking like the fact, for example, the sphere's volume is 4/3 pi r cubed, and then its surface area is 4 pi r squared?
Sort of, yeah.
Okay. No.
Okay.
No, that's not going to work out. So what we are going to do is we're going to do a triple integral. We are going to set this thing up with a triple integral and basically approach it the same way where we think about integration man. We're going to choose a direction for integration man to stand first. figure out which surfaces are determining feet and head. And then once we do that, we're going to look at the shadow of this shape in the coordinate plane of the other two variables and set that thing up the usual way with double integrals. Okay, so I'm actually going to show you multiple ways of setting this one up, just so you can kind of see that you can adjust your viewpoint however you'd like. But I'm going to recommend that we start with a dz. And so just because it works pretty well, let's do dz, dy, dx. So this volume is going to be a triple integral of dz, dy, dx. And so now the question is, what are the bounds for z first? All right, so now think about integration man. He's going to be standing up in the z direction. So that means integration man is going to be standing upright like this. So as he's walking around in this volume, what's determining his feet? Which surface?
The XY plane.
Okay, so it's the XY plane. So what is that as a z equals? Okay, so Victor just put here, so z equals 0, and then you put z equals 6. Let's not worry about the z equals 6 just yet. But I definitely like z equals 0. That's the XY plane. And he's always walking on the XY plane. So the lower bound for the z's is going to be 0. Okay, so now as he's walking around in here, what surface is his head running into?
The top vertice of the shape.
Okay, well, that's going to be when he's in that corner. But what if he's further out this way? His head's not going to hit that vertex, right?
It's good. The one on the left with respect to us is the ZX plane.
So the one on the left is the ZX plane, yeah. But that's not where he's going to be hitting his head. Okay, you know what I'm going to do? I'm going to go mobile on my camera here for a second. Because I want to look in the corner, right? So here's how I want you to picture this. Okay, so actually, you know what? Let's be smart about this, Bruce. Okay, so now you can see my really boring office. We just moved in not too long ago, so you notice that there's nothing up on the walls. In fact, you can see the stack of all of our paintings that are going to go in their random places wherever we finally decide. But anyway, it works pretty good as a classroom. But here's how I want you to picture this. So you see that corner down there? That's the origin, right? Just like in this picture right here, that's that corner. So you see the wall that's got the outlet, one that's over here. So this line right there is the x-axis. This line is the y-axis. And so the groove between the walls, that's your z-axis. All right, so are we all on board? You visualize that? We good? Thumbs up?
Yeah.
Yeah, okay. So come back to our picture. So that corner, this is the corner of the room. This is the wall that has the whiteboard. This is the wall that doesn't, has the window. And then of course, this goes up towards the ceiling. All right, so now what we've got, here we go, hold on one second here. Let me grab one of the things that has yet to go up on the wall. Okay, so here's a plane. Just so you guys know, that is a map of the Puget Sound, San Juan Islands up in Washington State. That's where I grew up, so that's why I've got this mounted. But anyway, so we've got a plane that's now resting like Well, I can't quite get it right, but it's kind of wedged up in the corner like there, right? So this is the point 0, 0, 6. We follow it down to the point, what was it, 2, 0, 0. And then there's the other point over here that's 3, 0, 0. Okay, so now think about integration man. If he's standing upright, where's his head hitting as he's walking around?
On that plane.
On this plane right here. His
Yes.
head is bumped against the map. No matter where he's walking, right? Because, let me move this again. There's a triangle down here. Hold on one second. Okay, I just had to make a line. All right, so there's a triangle down here that plane is resting over, right? So here was the 2, 0, 0. There's the 0, 3, 0. And then there's another point up here, right? But integration man is walking around in this triangle, right? He's just going to buzz around in this triangle. But that plane is slanting on top. So if he's standing up vertically, his head is always hitting that plane. So if we come back to our picture, his feet were always on the plane, the XY plane. They were on the floor, but his head's going to be butting up against the plane that's at an angle. All right, so does that make a little more sense? Do we kind of see what's going on here?
Yeah.
All right, this is going to be the challenge, by the way, with these, is visualizing 3 dimensions and visualizing the space. If we were together, if this class was actually going on in person, what I always do is I always give you a gift this day, give you a present. So I'm sorry, I'm not going to be able to give you this present. But don't get super excited, because all it is a little container of Play-Doh, modeling clay. Get a little thing of modeling clay, right? Play-Doh or, you know, a cheaper variety, doesn't really matter. Because you can use that to help you construct these things. And then you've got a little model in your hands and you can bend it and you can twist it and you can try to picture looking at it in different ways. So I highly recommend getting something like that. Again, unfortunately, since we're not together, I can't do that for you. Anyway, so let's come back to this. So his feet were on the XY plane. His head is on this slanted plane. So that means we got to get the equation of that plane. Uh-oh. So how the hell do we do that? All right, Victor, you're right. We do have 3 points.
I forgot, Bruce.
What's that?
I forgot.
Yeah, you forgot? Okay. So 3 points is enough. So what we're going to do is we need to make 2 vectors. Good. Oh, it looks like Victor totally remembers this. So we're going to find 2 vectors. And then what do we do with those 2 vectors? Good. You cross them. All right. So here we go. One of the vectors. Let's look at the vector, say, that connects these 2 points, 2, 0, 0 and 0, 3, 0. All right. So to get from 2, 0, 0 to 0, 3, 0, I'm going to call this guy V. I need -2, 3, 0, right? To get from 2 to 0, I subtract 2. From 0 to 3, I add 3. From 0 to 0, I do nothing. So then I need another vector. Let's call it, say, U. Let's do the same thing going from 2, 0, 0 to 0, 0, 6. It doesn't matter which 2 points you choose. Well, that one is going to be a -2, 0, 6. Right? Again, the x coordinate goes down 2, the y coordinate doesn't change, and z goes up 6. So those 2 vectors are actually the 2 vectors that form these 2 sides. But if we cross them, that's the normal vector to our plane. So let's do v cross u. That's going to give us 18 for the i's, For the j's, we're going to get 0 minus a negative 12. That's 12. And then for the k's, we're going to get 0 minus a negative 6, which is 6. And what I know is that this is a normal vector. All right, so that one's normal to the plane. I'm going to simplify it a little bit.
Hey, Bruce,
Yeah,
could you label which is V and which is U on the graph?
sure. V
I forgot.
is this vector, and U is that vector.
Thank you.
You're welcome. So if 18, 12, 6 is normal to the plane, then any multiple of it is. So I just divided by 6 to make the number smaller. Okay, so now that we got a normal vector, how do we get the equation of the plane?
Don't we have to parameterize it?
Now it turns out we don't. Okay, so Victor started writing x minus a, y minus b. All right, so let me give you a couple of approaches. One is you can take those guys, take these components of our vector, put those as coefficients on x minus x naught, y minus y naught, z minus z naught, where x naught, y naught, and z naught are a point on the plane, any point you want, and you set that equal to 0. So like in this case, if we were to take, say, the point 2, 0, 0, we'd go, we've got 3 times x minus 2 plus 2 times y minus 0 plus 1 times z minus 0 equals 0. And if you were to distribute this all out, it would be 3x plus 2y plus z equals 6. So that's one approach, and that always works. I find it a little bit faster if you recognize this. Notice that in the end, we've got 3x, 2y, 1z. That was these right here. So as soon as I get my normal vector, I immediately write 3x, 2y, 1z. Or if our normal vector was minus 2, 0, 6, it would be minus 2x, 0y, 6z, or whatever it happens to be.
And that's true every time?
Every time.
Cool.
With your normal vector. But then we have to figure out what that number is, right? So that doesn't tell me anything about that 6. But what I do know, like I would start with, I know it's 3x plus 2y plus z equals. And then all I do is I pick one of my points and I plug it in here, and I see what number I get. So for example, take 0, 0, 6. If I put 0 in for x, 0 in for y, and z in for, or 6 in for z, what do I get?
Z equals 6.
I get 6. What if I did it with 0, 3, 0? 0 for the x's, 3 for the y's, 0 for the z's. 0 plus 6 plus 0, 6. How about 2, 0, 0? 6 plus 0 plus 0, 6. That's what I do, so I don't have to actually remember a formula or do the algebra or anything. I just take the normal vector components, make those the coefficients of my x, y, and z, and then pick a point and plug it in, see what number I get, and you're done. Okay, well, at least we got the equation of it now, which is good, because we need that to form the top, right? This plane is where integration man's head is hitting. But I can't put it in like this. I have to solve it for one of the letters. So which letter do I solve it for?
Z.
Z, because we're doing a DZ first. If we were doing it in a different way, like let's say it was a DY first, if we were running into that plane, I would solve it for Y. If we were doing a DX and integration man was bumping into it, I would solve it for X, right? So basically, once you get the equation, you have to decide, well, which letter do I solve for? And that's going to depend on what differential you're using, which variable. All right, well, if I solve that for Z, that's going to be 6 minus 3x minus 2y. So there are the bounds on my Z integral. All right, now before we move on, before we try to attack the other two pieces, questions. Are we all right?
So I understand that U cross V gives us a normal vector that is normal to the UV plane, right?
Yep.
Okay.
Correct.
I'm curious why we want the UV plane and not, I thought we're looking for the plane that if we extended U in the Y, in the positive Y and negative Y direction, does that make sense? That's what we're looking for?
Okay, no, what we're looking for, remember when I put everything in the corner? We're looking for that, the map,
Mm-hmm.
the map plane.
And I thought the map went in the direction of U.
It does, but it also goes in the direction of V, and it also goes in the direction of this guy W. You wanted to call this one another vector.
Okay.
V and U both lie on that plane. Like if I were to bring that map back up, okay, so here's our map. Here are V and U.
Right.
They're in that plane. W would be the one that's over there, right? Like this blue triangle, imagine that that's just a blue triangle drawn on this plane.
I see. Yeah, I understand that.
So basically, we're just cutting that plane until we see only the triangle, but that triangle lives in that plane.
Okay. Yeah.
So in essence, what we did was we found two vectors in the plane, those two guys.
Yeah, I guess I just don't really understand the shape of a tetrahedron too well, because in my eyes, wouldn't integration man's head be hitting 3 different triangular planes throughout his ventures?
Nope. Because again, so if I'm in here, sorry about that. So I'm in here. I'm integration man.
Mm-hmm.
I'm going to walk around in a triangle, right? Are you cool that there's a triangle on the ground?
Yeah, your feet are on one triangle. Yeah.
Yeah. So I'm walking around in that triangle doing whatever. But the other shapes of this tetrahedron are the wall behind me.
Oh. Okay, I understand. Your head, if you're at the origin, is on the highest point of the tetrahedron.
The highest point, yeah, is above it's above the origin.
Okay,
Yep.
I understand.
So again, remember this tetrahedron has 4 sides. So in my room, 3 of the 4 sides are the floor, the wall behind me, and the wall to my left, your right. Right? So those are 3 of the sides. The 4th side is coming down this way. I had to change my axes so that I'm tall enough to get under it, right?
I get it.
But it's sloping down like this. So my head will never hit the wall behind me because I'm standing straight up. just like my head will never hit the wall on my side because I'm standing straight up.
I
But my
gotcha.
head will always be hitting the sloped plane.
Okay, that makes perfect sense. Thank you.
Does that make sense now?
Yeah.
And then my feet are always on the floor. So that's why I'm good with going from 0 up to that plane. So what we needed to do was find 2 vectors in the plane, 2 vectors in that slanted plane, which I just used those blue lines that were connecting the vertices, right? Get my normal vector, and then I can get to my equation.
Perfect. Thank you.
All right, cool. Good question, though. Any other questions? All right, so we got our z bounds. Sweet. Now we need to get our x and our y bounds. So what we need to think about now is, suppose that there's a big bright light shining down above, right, in this positive z direction. What's the shadow of this tetrahedron? What part of the xy plane is covered up by this tetrahedron? Well, let's draw an xy plane real fast, like we're used to. Here's x and here's y. Now we know we're going to be in the first quadrant, right? Because this tetrahedron is always in this portion. Like, I'm not going back behind the wall or anything. So it's always going to be in the first quadrant. I know that it goes out as far as 2, 0 in the x direction, and in the y direction, it's going to go up as far as 0, 3. And this line, the one that was the vector v, was on that line, actually is the line that connects those 2 points. So this is that triangle that we saw on the ground, right? Remember when I made my pens into another length, another side? That was this green line. This was the corner of the room. This was at the base of the floor underneath the outlet, the electrical outlet. And this was at the base of the wall on the other side. Yeah, we're okay with that?
Yeah, it's where integration's man feet are, right?
Yeah. So integration man, hold on a second, I'm setting this up again for you. So integration man okay, so there is that same triangle. Just we have to rotate our worldview a little bit. All right. This is the point 2, 0, because here's the x-axis. So that's the point 2, 0. That's the point 0, 3, because this was the y-axis. And so this line right there is this line right here. So you see how I've got my pens such that the writing ends are kind of up here, pointing that way. Right? So the writing ends are always up in there. Well, if I just take that, reorient it, it's this direction. So I've got a triangular region over which integration man is walking. And that's that triangle. So for the x's and y's, it's the same thing that we always did before. Now let's look at integration man in here. So do you want, which way is integration man going to be, vertical or horizontal, according to the way that I've got my
Vertical.
set up? Yeah, I think I heard it. It's going to be vertical. Got y equals. So thinking about integration man vertically in here, what determines his feet and what determines his head?
His feet is x equals 2. Or
Not
I
x
guess
equals
y equals 0.
y equals 0. There we go. So his feet are at y equals 0. They're on the x-axis. And his head?
The slope of that, well, the equation of that line.
Okay, we need to get the equation of this line right here. All right, well, its slope, we're going down 3 and over 2. So that means that the slope is going to be a minus 3/2. And the y-intercept is 3. So we get y equals negative 3/2 x plus 3. Okay, and then what about x's? What are the x's going to range from?
0 to 2.
0 to 2. All right. These are rough. These can be really, really challenging. And like I said, it's all going to come down to visualizing this thing in 3 dimensions. And, earlier, Seamus said something that I want to bring back. Remember, he said, I guess I just don't really understand, or he said something like, I can't picture a tetrahedron, right? That may not be verbatim, but it was something along those lines. And that is the challenge. So when you read this stuff and you read one of these problems and they say, we're trying to find the volume, underneath a paraboloid given by whatever. If you can't picture a paraboloid, it's going to be really hard to do these problems. So I'm going to definitely recommend you go back and you look. I think it's in chapter 3. It was definitely one of the chapters that we skipped this course because we did it in the fall or in the spring. And go back and look at the different surfaces, ellipsoids, paraboloids, hyperboloids, right? All those good things. Go back and look at those because it's going to definitely help you if you see them and you can start picturing them in your mind, right? Like if you see hyperbolic paraboloid, I don't know if you guys can envision that, but that's the one that looks like a Pringle. And if Larry didn't talk about Pringles last quarter, shame on him, because that's like the best example, right? The hyperbolic paraboloid, those are the saddles, but a Pringle chip is totally in the shape of a hyperbolic paraboloid, right? Or if I say ellipsoid, if you don't immediately start thinking the shape of like an M&M, right? Peanut or plain or otherwise, right? That will definitely help you. So go back and review those because visualizing the shape is at least 75% of the battle. All right, well, now that we've got it set up, let's do it. Let's figure out what the volume of this shape is. All right, so we're just integrating 1, so that's going to be nice and easy. That gives us a z. And so when we plug in our bounds for z, we're going to get 6 minus 3x minus 2y minus 0, so just that, dy dx. All right, now we're going to integrate with respect to y. So we're going to get 6y minus 3xy minus y squared. And we're going to evaluate that from 0 to minus 3/2 x plus 3. Okay, well, let's plug in those bounds. The 0 we don't have to worry about, right? Because that's just going to make all that go away. The other one, when I plug in for y, I multiply by 6, I get minus 9x plus 18. When I multiply by minus 3x, I get plus 9/2 x squared minus 9x. And then I'm going to subtract that thing squared. Well, when I square that, I get 9/4 x squared minus 9x plus 9. So let's group like terms before we attack this. So x squared, I've got 9/2 minus 9/4, so that's 9/4 x squared. X is minus 9x plus 9x, I believe leaves me a minus 9x. And then constants, I've got 18 minus 9, which is minus 9. So let me just run this over here real quick. So now when I integrate that, I'm going to get 3/4 x cubed minus 9/2 x squared minus 9x, evaluated at 0 and 2. So that's 6 minus 18 minus 18, and I messed something up somewhere. Crap. You know how I knew I messed something up?
No.
Negative answer, and it's all above
Yeah.
the.
Be a negative,
The
and this is
origin.
a volume. Volumes can't be negative. 6y, 3xy minus y squared. Okay, I like my integral. Minus 9x plus 18. That's definitely right. Plus 9/2 x squared minus 9x. Okay, that's definitely right. When I square that thing out, FOIL is going to be 9/4 x squared. Outside and inside are both minus 9/2, so that gives me minus 9 plus 9. That's definitely 9/4 x squared minus 9x. Oh, this is plus 9. 18 minus 9 is plus 9. Okay, I'm much happier now. Okay, so this ends up giving me 6. Whew. All right, so it turns out that the volume of this parallelepiped is 6, which is definitely not half of the volume of the box that it sits in, right? Because if we were to extend this to a full box, we'd have width or dimensions 2, 3, and 6. And 2 times 3 times 6, that's 36, which is definitely not 6. All right, so moral of the story is the volume of that tetrahedron is 6. And now we were able to find it using a triple integral. And I know what you're thinking, at least some of you. You're probably thinking, Jesus Christ, this is like the most basic, easiest shape there is in the world, other than a cube. And yet it was still this brutal. What's going to happen when we've got tops that are, you know, parts of spheres and bottoms that are paraboloids and Lord knows what else? It really just comes down to setting it up, because once we get it set up, honestly, like from this stage on is what I call monkey math. Those of you who know me know what I mean by that. Monkey math is math that you can teach a monkey to do. Don't be offended by this either, because that's not like, oh, you're just barely smarter than a monkey. No, it's like there isn't thought anymore. It's just process, right? It's just procedure. You just do it. That's what I call monkey math. And so once it's set up, we don't think anymore. We just do. But setting up those bounds, this is why calculus is not monkey math altogether, because you need to be smarter than a monkey to picture this, to set it up properly. But once you're there, it's good to go. Trust me, they get easier the more of them you do. And everybody is overwhelmed by it at first, just because we're not used to picturing stuff in 3D so much. So to thoroughly confuse you, yeah, I got enough time to do this. To thoroughly confuse you, let's change the order of integration on this. Instead of doing dz, dy, dx, let's turn it around so that we do it in a different orientation. All right. In terms of which orientation, I'm going to erase the answer here. We've all got it, right? That's 6. But this time, how about we set it up as a I'll tell you what. Give me a letter. Give me either X or Y. First one I hear or see in the chat box.
X.
All right, X. So we'll do a DX, which then leaves me either Y or Z. First one I hear or see.
Z.
Z. All right, cool. So we'll do DX, DZ, DY. So we're going to get it set up with this different orientation. All right, so the reason I asked you guys to give me something other than Z first is because I wanted to not do DZ first. But then once that happened, it's whatever order. All right, now we don't need to worry about this U and V anymore, because we already used those to create our equation for that plane. So we already know the equations of everything. But now we have to think about if integration man is oriented this way, where are his feet and where is his head? Where does his head reside? All right, so if we're doing dx, that means integration man is going in an x direction. So as he walks around, his head is always going to be pointing towards positive x. So think about my room again. Think about my room and think about the 4 surfaces here. So we got the floor, the whiteboard wall, the window wall, and the slanted plane. Which of those 4 is integration man's feet going to be on the entire time?
Window.
The window wall. Right? He's walking on the wall. So he's walking on the wall. So what's the equation of the wall? What's the equation of this plane over here? And I'll give you a hint. It's either x equals 0, y equals 0, or z equals 0. This is one of the coordinate planes.
X equals 0.
Give me x equals 0. Because the y's and the z's change, the x doesn't. So his feet are going to be on x equals 0. Okay, so now he's walking around in there. What surface is his head going to be bumping against as he walks around?
The angled triangle, the painting.
Yeah, the angled plane, right? So that angled plane, the one that I had, yeah, the map I had, right? That one is where his head's going to be hitting the entire time. So that means I need to use that same plane, but instead of solving it for z, I need to solve it for x. So just to recall, the equation of that plane was 3x plus 2y plus z equals 6. If I solve that for x, I'm going to get 1/3 6 minus 2y minus z. Right, just solve this thing for x. Move the 2y and the z, and then divide by 3. So if we had started with a dy, his feet would have been on the whiteboard wall, and his head would have still come up and hit that slanted plane. We just would have solved it for y.
Is
So
it
believe it or
purely
not, the tetrahedron is still a really nice and easy shape because his head is always on that slanted guy. But I'm
that
sorry.
won't? Oh, it's okay. It won't always be the case where the plane might change, right?
Or you mean there might be times where the plane could change, where it goes to a different surface?
Correct. Yeah.
Yeah, it definitely can happen, not with this tetrahedron though.
Okay.
It's really because the three sides are coordinate planes that we're using both the front and side wall and the floor as three of our surfaces. That's why it worked out that we're always bumping our head against the slanted plane. All right, so far so good, I hope. But now we need to figure out, okay, what portion of the wall is he walking on? And that's really this triangle right here. So let me redraw planes, but this is going to be the YZ plane. And if you think about the triangle that's formed by the intersection of the slanted plane and the YZ plane, it's got a point up here that's 0, 6, and it's got a point over here that's 3, 0. So that's just coming from these right here, right?
Feet on
so-
z equals 0.
I'm sorry?
Feet on z equals 0.
Mhm. Right, because we got the origin there, and this is all x equals 0. We're all in that plane. But it's kind of like when I set the painting against the wall. Remember how the edge of the frame formed a line against the wall? That's this. That's the line that we would see, right? Like if I were to start drawing this on the wall, I never would because my wife would, But if I was at the college, I'd probably do it because, whatever. But there's that line on the wall. That's this line right here. And so now, since we're doing a DZ, integration man needs to be vertical this way. So his feet are always going to be on z equals 0, and his head is going to be on that line. So what's the equation of that line?
Six minus 3x minus 2y. Oh, no, never mind. It's much easier than that.
-2, right?
So we're going to have z equals, the slope is -2, right? Going down down 6 over 3. So minus 2y
Plus 6.
plus 6. Just saying it's y equals mx plus b. It's just the roles of y and x are now z and y respectively. Okay, so then I needed that as z equals. All right, well, it is z equals. So it's going to be minus 2y plus 6. And so then lastly, how do the y's range from what to what?
0 to 3.
0 to 3. So this should also give you 6. If you evaluate this triple integral, it should also give you 6. All right, well, this is just a second way that we could do it, but there are actually 4 more. There are 4 more combinations of these that we could set up. I'm not going to do all of them, but this is where it starts getting a little bit crazier, right? Single variable integrals, 1 way. Double integrals, 2 ways. Triple integrals, 6 ways. If, and this is an if because we're not gonna, but if we were going to do a quadruple integral,
12.
24 ways.
Oh,
24 different ways to do quadruple integrals. So those numbers, 1, 2, 6, 24, I don't know if you recognize that pattern, but those are factorials. So whatever your integral number is, it's that many factorial, different options. So if we did a quintuple integral, so 5, there'd be 120 different ways that you could set it up. All right. Well, I mean, that's good and bad, right? Like for these triple integrals, we've got 6 choices. We've got a lot to pick from, so we can find the one that works best for us. So that's actually the big plus, is that we get more options. But the minus, the real con is we have more options, right? Like we claim to like to have choice, right? Especially here in America, right? We like choices, we like personal freedom. But I'll tell you what, in math class, you don't like choice. You don't. You want me to tell you, do it this way. Because if I tell you, do it this way, and you learn that way, you're good to go. Right? It's as soon as I give you options that things start going, whoa, wait a minute. Well, that's why all of a sudden you're starting, whoa, wait a minute, I got 6 choices. How do I figure out which one to use? And how do I figure out which one is best? And that comes with practice. We'll definitely see more of this. Don't worry. I'm not like never showing you another triple integral. We're going to be doing lots of these next time. But we're going to continue doing triple integrals. And you'll see that sometimes there's a natural choice. Sometimes there isn't. Sometimes it doesn't really matter. And we'll kind of go from there. So Victor, you just said, do you still have polar with triple integrals? Oh, that's a really good question, right? You saw that we could use polar to help us with double integrals. The answer is kinda, except we don't use polar because polar is really just for 2 dimensions. But you guys know some other coordinate systems for 3 dimensions, or should know, or should have at least heard of them.
Spherical and cylindrical.
Yeah, spherical and cylindrical. So remember that there are some other ways of looking at the 3D world. Well, we are, and this is coming, we are going to at some point go, well, what if we want to convert it to cylindrical or spherical? What if I want rhos, phis, and thetas? What if I want z's, r's, and thetas? We can do that. Just like with the polar, we're going to have to do 2 things. We're going to have to convert everything to the new system, right? So like if we're going spherical, we have to change all the x, y's, and z's into rhos, thetas, and phis. And if as I'm saying this, you're like, holy shit, I have no idea what you're talking about, go back and look at spherical and cylindrical, but we'll also talk about it when we get there. Anyway, so you're going to have to convert everything, but then also we're going to have to change our dv. Because just like when we went to polar, remember how the dA wasn't just dr and d theta, we had to throw in the extra r. We're going to see the same thing happens when we go into cylindrical and spherical. There's something that we have to put in addition to just the dz, dr, d theta, or the dz or d rho, d theta, d phi, right? We're going to have to throw something else in there. So, but I kind of like how you were thinking there, Victor. Yes, we're going to be able to do similar things. And the hope is that that actually does help us, which it will, again, specifically for certain solids in space. So what we're going to do on Friday, I know that it says on the syllabus that we've got a quiz coming. We're not going to do a quiz on Friday. I haven't been able to get stuff graded back to you, and I don't want to dump another quiz on you and get more backlog myself. So early Halloween present, right? So it's not a trick, it's totally a treat. No quiz on Friday, okay? So what we're going to do is start at usual time, right? So instead of usually on a quiz day, we start a little bit later. We're going to start at 1 o'clock like normal, and we're just going to do more triple integrals, okay? So if you've got some sort of modeling clay, Play-Doh-y type stuff, I definitely recommend getting it out. If you don't have any, maybe you can, get some when you run to the store or something. It's obviously not necessary, but it can be helpful when we're trying to visualize this stuff. And I will do my best to try to help you see it through this mode. I'm glad I was able to actually kind of figure out how to show you a trapezoid by looking in the corner of my room. I will try to do that, continue to give you models in here that you can see. I don't know if it's going to be as effective as if we were in the classroom, but we'll do our best. All right. So it all comes down to visualizing this, solid in space, this region over which we're integrating, because that's the hard part. Once we've got the bounds, integration is integration, man. Get it? Integration. Integration is just integration. So it's not that big of a deal once we get it set up. The battle is getting it set up. All right. So with that, I think I'm going to say adios and stop our recording. So I will see you all on Friday.